In previous sections, we discussed the multiplication of vector by scalar and addition and subtraction of vectors. And I mentioned that there are two ways of multiplying vectors. One of them is called the dot product. Another one is the cross product. In this section, we're going to deal with the dot product. The dot product of two vectors A with components A1, A1, A2, and A3, and B with the components B1, B2, and B3 is defined as A dot B. A1 times B1 plus A2 times B2 and plus A3 times B3. I'm writing these for three-dimensional case. The idea of introduction of the dot product in two-dimensional case is similar. Let's consider an example. Find the dot product of A equals to 3, -1, and 2, and B, which is 1, -2, and 1. Solution. Based on the definition, so A dot product with B is A1, B1, A2, B2, and plus A3, B3. So we need to multiply corresponding components and add the results. So we get A times B is going to be equal to 3 times 1 is 3. Let me write that thing down. 3 times 1 plus -1 times -2 and plus 2 times 1. So that is going to be equal to 3 plus 2 plus 2. That is ending up being 7. When we discussed the multiplication of a vector by scalar, and addition and subtraction of two vectors, the results of those operations were always vectors. As you can see from here, from the example, the result of the dot product is the scalar. So remember that this is a very important part. So the result of the dot product is a scalar. Also taking into consideration that it can be positive, negative, or 0. So it is either positive, negative, or 0 number. Let's consider some properties of the dot product. The first important property say that if you're multiplying a vector by itself, the dot product of a vector by itself is equal to the magnitude of that vector raised to the second power. Let's prove that. So if the vector A has components A1, A2, and A3, then we get A1, A2, A3, dot product with A1, A2, A3. That is equal to A1 squared plus A2 squared and plus A3 squared. And you see that this is nothing else but the magnitude raised to the second power. So this is the magnitude of the A raised to the second power. The second property that's important for us is the so-called distributive property. So if you're multiplying it, if you're dot producting the A with the B plus C, then you can actually multiply A with B and then add the product of A and C. let's show that this is also true. So we're going to work with components of each vector and see what we're going to have. So we have A1, A2, A3 for the A, and the expression in parentheses is going to give us B1, C plus C1, B2 plus C2, and B3 plus C3. Multiplying the expressions, we get A1 times B1 plus C1 plus A2 times B2 plus C2 plus A3 times B3 plus C3. We can distribute and get rid of parentheses and then regroup. So we get A1 B1 plus A2 B2 plus A3 B3. And then we can write A1 C1 plus A2 C2 and plus A2 A3 C3. So the first set of parentheses is just A times B, the dot product of A and B, and the second set of parentheses give us the A times C. That proves the property that we have. Now, the third one is the property that we're going to use to prove some results, and it is about the square of binomial. If you remember that formula, the square of binomial is like if you have a minus b squared, it's a squared minus 2ab plus b squared. Same kind of idea works here, but we're going to use the property A and property B to prove these properties C. So let's see. So A minus B squared is just dot product with A minus B. So it's A minus B times A minus B. Foiling these, we get A dot product with A minus A dot product with B minus A dot product with B. We can always switch the order in the dot product. So, and then we have plus B dot product with B. A times A is going to give you the magnitude of A squared according to this first property. Then we have 2 A dot product B, and then we have magnitude of B squared, again according to the first property. So this proves all the three properties. We will discuss more properties in upcoming videos, and we'll dig deeper into the dot product and its interpretation in terms of vectors and geometry.